So we have another AMC 10A problems, and some of them also 12A. So this one was number 6 on 10A. So we want to find the minimum number of successive swaps of adjacent letters in the string A, B, C, D, E, F that are needed to change the string to F, E, D, C, B, A. And then we are given an example of 3 of those letters, A, B, C to C, B, A. And we are told that's going to happen after 3 swaps. So like usually if they give us some examples, we really need to take advantage of that because that's going to give us what they really mean if you are not really sure what's going on. So that might be the good to kind of start with to understand before you try the problem. So we are given ABC, for example, right? And then you can like get BAC. What happened? You just swap A and B. So that's BAC. And now they swap C and A. So that will be BCA. And now they swap B and C. That will be CBA. So, and if you try your best to make it a bit like shorter than this, you really cannot. This is the list we can like do in terms of swapping, which is 3 times. So that's what we are given. But if you really don't know what to do to get these 6 letters, because 3 to 6 kind of a lot different. So, and then when you look at the choices, we have like at least 6 and then maybe 24. So that's why it's kind of harder to list them as well. So which is why you would probably want to start with some simple case and see if there's a like pattern going on. So that's the usual approach. So let's start with like 1 letter, but if I start with 1 letter instead of 3 letters, there's nothing. I cannot swap. It's just immediate sound, right? So which is why it doesn't really help. So, but if I have 2 letters, let's say A, B, and if I want to make this into BA, right? There's only 1 swap needed. So you just swap those 2 letters. That means this is one swap. Okay. But if I have ABC, which we are given, and if you want to make this CBA, so we know that this is gonna require 3 swaps. And this is what we have, but let's kind of try to see if we can make a general statement from these 2. And if we cannot see, we maybe list the 4 version as well. And then if that does give us something, we can try that. So what I'm trying to say, if I have A, B, C, D, and then the goal is to get D, C, B, A, right? So then we can just kind of make that 6 or even 10 letters, so which is not a big deal. But you know, in the first one, to get this like BA, we have to take this A and move it 1 unit to right, which is like, which was enough because when you move this, that will move that way, then we are good. But for the second one, you know, we need to move A 1 to the right, but it wasn't enough. We need that A 1 more time, which means A has to move to the right twice. Okay. The same thing when you move that, so you know, we need to move C this way and this way. But of those moves, like when you move this C right here, okay, so you swap something, but you don't want to swap B because B is going to be in the middle. So, and then you're going to move this 1 more time. That looks like C is moving twice and then A is moving twice, but one of those swaps are actually identical. Like A and C are switching, which means that move should be count 1 lesser. So for this case, I will say we have 2 moves for A is required to move all the way to the dislocation. But for C to move this location, we need 1 lesser move because one of those moves are actually counted already in this 2, which is why we got this 3. So I hope that was clear. And if that like wasn't, so make sure you like take a look at it a bit more. That's what we have. And the same reasoning, if you move this A all the way to D, so you need 3 moves. And then for the like B, so I need to have like 1 moves, right? And then for like D, you need like 3 moves as well. 1, 2, 3. But one of those like moves was going to be counted with A's. So which is why we don't have to count that twice. So that could be written like 3 moves needed for A, and 2 moves for D, because one of those moves are counted already. And for like B, we need to get this to be here, right? So you can just get one move. So that should be one more move. So that will be 6 moves. So this is what we have. So it looks like we have 6 swaps for this guy. And based on this kind of reasoning, like these numbers are actually the numbers that we've seen a lot. These are our triangular numbers. And if you don't know about what that means, you can just kind of remember, I don't know, the sum of the first integers. If you kind of know the Gauss formula, that's actually give us those numbers as well. So the triangles numbers are the number of like the dots that needed to make a triangle. So if you want to make a dot, that's one triangle. If you need a, let's say a triangle with 3, so that will be another triangle, or you can have something like this, like 3 by 3. So if you count those 1, 2, 3, so that should be 6, and that's called like triangular numbers. But anyway, so but how do you get with the 6 letters? So when you have 2, we have 1 swap, which is the first triangular number. When you have 3 letters, that's the second triangular number. If you have 3 letters, you have the third triangular number. I mean, and then 4 letters, the third. So which means if you have 6 letters, you are gonna find the fifth triangular number. Number, right? So how do you find that? So you just add 1, 2, 3, 4, and 5. So you can add them. So you can just use the Gauss. So that will be 15. So I hope that was clear. So this is really common question, I would say. Even last year, I remember AMC has a question similar to this one. So it was one of the early problems as well. But anyway, so that was number 6. So let's take a look at the next one. Okay, number 7. The product of 3 integers are given 60, and we want to find the least possible positive sum of these numbers, these integers. So like we have to be careful because it says the sum has to be positive, but it doesn't mean the number should be positive. Like we can have some negatives as well, maybe all negatives. So it depends on the problem. But let's see, like if you want to take the 60, so that would be 15 times 4. So that's my prime factorization. So if you want to get the smallest sum, you can try to get those numbers as small as possible. So you can say 3, 4, and 5. And the least possible sum looks like 12. So which means we can immediately cross this if they are all positive. So that's 12 is possible anyway. But we need to try if this is something better than this possible. So like if I try like maybe 2 negatives and 1 positive, because we need 3 numbers, right? So we are told there should be 3 numbers. And if you try like 2 negatives and 1 positive, so then might be some will be the smaller than having 3 positive. So, but when you take any 2, like say you want to choose these 2 negative, that will be -7 plus 5, -2, but we cannot get negative, so it doesn't look like that working. But we don't have to take only these numbers. We can choose like 1, maybe 2 and 2, and like depends on what you need. So like I can say, so I can write 2 times 3 times 5, and we can multiply a bunch of 1s if you want to, but let's just remember that. So the thing is, you know, if I take these 2, that's 10, and then I have 3 and 2, which is another 2 numbers. Like if I want to take -2, -3, and 10, so that's 5, -5, that's 10. That looks like 5 is possible. So D is not the case. But if there's a way to get the way better than this, we should try hunting for that as well. But I took 10 because I multiply 5 and 2, but maybe I can multiply 2 and 3, which would be 6. If I do that, so you will get 5 and 2 alone. So that should be the case. But in this case, if I take these 2 negatives, so that will be -10 and like 6, which is -4, which is another positive number, so which doesn't work. But maybe we can try a little bit different. So I can still try 10. because it looks like we are like getting dead end from here. So if I try 10 here, but maybe combine those two, which is going to be 6, and I can have 1 as well. So -1 and -6. So that looks like we have -7 and 10, which is add up to 3. So which is also way smaller than 5, so which is possible. But if you try something else, like there's no way to get 2. So the B is the smallest positive number. So like, how do you kind of confirm that? Like since we are dealing with integer, you can just try all numbers that's kind of gonna give you the smaller sum, then go from there. But that might be something you can try. But this another approach in terms of the equation stuff, but I don't think we need for that because this is number 7. So no need that much work. Okay, number 8 is word problem again. So we have A, B, C, D. They work in a chocolate factory. And Amy, like I'm gonna use the initial A, B, C start at 1 p.m. Okay, so they start at 1 p.m. and we're able to pack 4, 3, and 3 packages respectively every 3 minutes. Okay, at some time later, the person did join the group, and this person was able to pack 5 packages every 4 minutes, and they finished together 450 packages by 2:45, right? So what time did the person did join the group? Like, okay, let's find, like it started at 1 p.m. for those 3 individual, and then it's ended at 2:45. So 1 to 2 is 1 hour plus 45, which is 60 plus 45 minutes, which is gonna be 105 minutes, right? The 3 people work 105 minutes. And we know that every like individual complete 4, 3, and 3 packages every 3 minutes. So if I divide this by 3, so that should be like 35 times these 3 individual work on. But every 3 minutes, they will work like finish 4, 3, and 3 packages, which is gonna be 10, right? 350. So those 3 individuals complete 350 packages in that time frame. So out of 450, which means the remaining 100 packages has to be done by person D, and the person D can finish 5 packages every 4 minutes. So if you divide this by 4, that will take us how many times those 5 packages will be done. So which we can multiply by 5, because every 4 minutes that person D can finish 5 packages. So that will be 125. So this is the minute that we kind of need to go back from 2:45, right? So that means this is gonna be 2 hours, 160, let me say 1 second. So that's 25, that's 125, 2:45. Okay, so that would be actually no, I should have 5 packages. Oh, 100 packages should be done. Okay, I did this part wrong. So, we are gonna need 100 packages that should be done by person D, but person D makes 5 packages every 4 minutes. So we just need the time for that person D. So that means 1 package is gonna take 4/5 minutes, right? And then since this is the number of packages that person they should finish, so we can divide this by 4/5 to find the time that is needed. So that should be 100 times 5/4. No, this is actually the same as what I just did, right? So that should be no. I'm not sure why so this has to be multiplied by 100. Okay, so we got this. 1 package should take 4/5 minutes. So we do have this packages, the 100 packages. So we should multiply this by 4/5. So that should be 20 times this, which will be 80 minutes. So which means the person D should start 80 minutes before the 2:45. If you take the 45 out of 80, you got like only 35 minutes. So if you take another 35 from 2, if you go back, so you got 125. So anyway, so that wasn't too challenging, but I kind of messed that part. So I hope that wasn't a big deal. But that was the number A. Number 9, so how many ways can six seniors form three disjoint teams, three different teams of 4 people so that each team has 2 juniors and 2 seniors? Okay, this is not too challenging. You just choose 2 people for each group, right? So like imagine like we have the groups are A, B, C, and we need 2 juniors from each group. So we have 6 juniors. I'm gonna choose 6, choose 2, and then I need 6 seniors for that as well. 6, choose 2 for this group. And then next one, I have 4 people left. 4, choose 2, and 4, choose left. 4, choose 2, and then the last 2 people goes to this guy. So 2, choose 2, and 2, choose 2. But the problem is, like if I multiply this, let's say 6 choose 2 is 15. And that's also 15. 4 choose 2 is 6. That's 6. That's 1 and 1. So I just skip how we get those because I assume everyone knows about the basic combination. So when you multiply this, you got these two 90 and then these two 90, which is going to be 8100. So which is one of the choices. But be careful because when we do this, we kind of did in a way that we carry the order, which, you know, the ordering of those teams, which doesn't matter because I said this is team A, this is team B, C, and stuff. So the order doesn't matter. We just like to make a group of 3 where each group has 2 from each like junior and senior group. So which is why we have to take that over counting, dividing by 81 like 100 by 3 factorial because we have 3 groups. So if you divide this by 6, I can divide by 3, that's 2, so that should be 2700, divide by 2, so that should be choice B. So that was number 9. So let's see the next one. Number 10 is interesting, but it's not really challenging either. So we are given the consider following operation, the given a positive integer n, which is if n is a multiple of 3, you replace that number by the 1/3. If not, then you add 10 to that number. And you just keep doing this operation until you get a pattern. For example, if you start with 4, since that's not multiple of 3, you just add 10 to this number to get 14. This is not multiple of 3 as well, so you add another 10, you got 24, but this is multiple of 3, you just divide by 3, you got 8, and you just keep doing this. And if you start with 100, what value results if you perform this operation exactly 100 times? So let's say we have 100, and after the first time you apply, I'm going to use this as 1 and then 2, right? So when you apply this, this is 100, and that's multiple of 3, so which means you're going to add 10, so you got 110, right? So, but this is the number you get after the applying the 1 time, so we don't count this one. If you, this is a number, like when you add a digit, that's 2, which is not a multiple of 3 either, so you will get another 10, which is 120. But when you apply the second time, you end up getting this. The third time, this is a multiple of 3, which is why we are going to divide this by 3 to get 40. And then you got like 40, which is going to be added 10. So you got 50, and then you got 60. So I hope that's clear so far. So if you keep doing this, you got 20 because it's multiple 3. So now you got 40, and then you got 20 because actually, no, you got 40 after adding like, I don't know, like 20 for like 30. So that should be 30 because we add 10. Now we divide by 3, and then we add 10, and then we add another 10. So we divide by 3 again. So that should be like 10. And then we add 10, we add 10. As you see, we are keep getting these 3 numbers. So after we hit 30, right? So 30, 10, 20, 30, 10, 20, 30, 10, 20, 30, 10, 20 will repeat. So that will be the cycle. But the first numbers wasn't the case. So this is 5, this is 6. So we want to find the number that we are going to get after doing this 100 times. But 30, 10, and 20 is one of the three choices. You can immediately class this, but you have to be careful because if you're kind of like getting 99 times or 101 times, so you're going to get one of those other choices. So we have 1, 2, 3, 4, 5, 6 so far. So we have 6 times supply. But after that, we are going to apply this some number of times, but that cycle will continue every 3 same terms. I'm going to say 3 times something. And then we want to get this to be maybe 100 or less than, let's say we want to get something larger than, less than 100 or equal to 100. Okay, so if this is the case, 100 minus this 94, so 94 is not divisible by 3. So if I try this guy to be 93 divided by 3 is like 31. So you got 93 plus this 99. So which means if you do this cycling 31 times after the first 6 numbers, after the first 6 operation, you get 99 terms, which will give us this guy as our 99th number, right? But after that, you need one more operation to get 100 times. So since the first number will be 30, so our answer should be 30 as well. So I hope that was clear. So that was just simple recognizing that pattern. Okay, so I hope that was all good. So I'll see you in the next video.